Topic introduces the two foundational approaches for estimating market risk: historical simulation and parametric estimation. Historical simulation estimates value at risk VAR directly from past portfolio returns without assuming a particular probability distribution. Returns are ordered from worst to best, and the chosen percentile identifies the VAR threshold. This method is intuitive because it reflects actual historical experience and captures non-normal behavior, such as skewness and fat tails. However, it assumes future market behavior will resemble the past and may fail during structural market changes. The program emphasizes that historical simulation is limited by data discreteness and sensitivity to historical sample quality. The parametric estimation approach differs because it explicitly assumes a probability distribution for returns, commonly the normal or log-normal distribution. Under the delta-normal framework, VAR is estimated using the portfolio mean, standard deviation, and a critical z-value corresponding to the desired confidence level. At a 95% confidence level, the critical value is approximately 1.65 for a one-tail test. Parametric methods are computationally efficient and easy to implement for large portfolios. They also allow analysts to estimate risk beyond observed historical losses. Nevertheless, the method depends heavily on distributional assumptions, and inaccurate assumptions about volatility or return distributions may significantly underestimate true market risk exposure. A key concept in these topics is value at risk, which measures the maximum expected portfolio loss over a specified holding period at a chosen confidence level. VAR provides a standardized framework for comparing risks across trading desks, institutions, and asset classes. For example, a one-day 99% VAR of $10 million implies that losses greater than $10 million are expected on only 1% of trading days. VAR became a global regulatory benchmark under Basel Capital rules because it summarizes market risk into a single, interpretable number. However, the program stresses that VAR only identifies a cutoff point and does not indicate the magnitude of losses beyond that threshold. To address VAR limitations, the program introduces expected shortfall (ES), also called conditional VAR. Expected shortfall measures the average loss occurring beyond the VAR threshold, thereby providing information about tail severity rather than only tail probability. ES is considered a superior measure during periods of extreme market stress because it captures catastrophic losses more effectively. The program explains that ES divides the tail into probability slices and averages the associated VAR values. Regulatory reforms under the Fundamental Review of the Trading Book increasingly favor expected shortfall over traditional VAR because ES better reflects systemic and liquidity-related market risk exposures during crises. The topic also introduces coherent risk measures, which extend beyond VAR and ES by satisfying desirable mathematical properties such as subadditivity, monotonicity, translation invariance, and positive homogeneity. A coherent risk measure evaluates losses using weighted averages of quantiles across the full loss distribution rather than focusing only on tail observations. This framework better recognizes diversification benefits and aligns more closely with rational risk management principles. The topic further emphasizes the importance of estimating standard errors and confidence intervals for risk measures. Since all estimates contain uncertainty, risk managers must assess the statistical precision and reliability of VAR or ES calculations before relying on them for capital allocation decisions. Finally, the topics discuss diagnostic and validation tools used in practical risk management. One important technique is the quantile-quantile QQ plot, which compares empirical return distributions against theoretical distributions, such as the normal distribution. A near-linear QQ plot suggests a reasonable distributional fit, while curvature indicates skewness or fat tails. The topics also highlight challenges associated with estimating confidence intervals for VAR, including data quality problems, non-normal return behavior, and model specification risk. During stressed market conditions, VAR confidence intervals often widen substantially, reducing estimate precision. Consequently, effective market risk management requires combining quantitative models with expert judgment, stress testing, and continuous model validation.